Thank you, Georg, for the warm welcome, and thanks for having me here. Maybe as a small disclaimer in the beginning, for those who have very strong feelings about memory roofline models, maybe take a seat just to avoid further medical issues. So I will play around with that a little today. Yes, and other than that, I'm talking today about pushing this roofline model. And this is work not only done by myself, but by my team. I'm blessed with a whole group of excellent people, and many of them actually contributed to this research. So I want to start with a motivation, and the motivation is basically the trend, what we see over the last decades in terms of processor development. What you see here is a couple of dots, and each dot represents one processor architecture. On the x-axis, you see the year of introduction, and on the y-axis, you see the machine balance of that processor technology in terms of floating point operations per memory access. And what you can see here is that you have like an upwards trend. So all the dots are arranged on an upwards trend. So what does that mean? That means that even though the performance is growing and the memory bandwidth is growing, the memory bandwidth is growing at a slower pace than the compute performance. And these processors are increasingly getting imbalanced in the sense that operations are more or less for free, but memory accesses is actually what counts and what often limits your performance. If we now pick a certain processor, what we can do is we can derive a roofline performance model. And this is maybe something different to what you usually see of how roofline performance models are derived. On the x-axis, I put down the arithmetic intensity in terms of flops per value, in terms of flops per data access. And on the y-axis, you then see the performance. And what you have then is that algorithms with a low arithmetic intensity, so algorithms that are in this region, they will probably not achieve the peak performance of your architecture, but instead they will remain in the bandwidth-limited performance area, and their performance might be significantly smaller than the peak performance of your processor. Then you have this knee here, and this is exactly the machine balance. And if you now have an algorithm that has an arithmetic intensity that is larger than the machine balance, then you should, in theory, achieve peak performance. Modulo, of course, that you have arithmetic imbalance and all these aspects. But in general, this is your upper bound if you have an arithmetic intensity larger than the machine balance. So for example, I have here an algorithm, and that algorithm is achieving on this computer peak performance because it has an arithmetic intensity larger than the machine balance. And the computer that I actually chose, or the processor that I chose, is the K computer, which was the fastest supercomputer in the top 500 list about 10 years ago. It was actually in Japan, and it was actually the predecessor of the Fugaku that is nowadays the fastest computer. If we now do a step and we move forward by a couple of years, we are at the Summit being the fastest supercomputer in the world. And the Summit supercomputer is based on NVIDIA GPUs, more specifically V100 GPUs. And this supercomputer and also the V100 GPUs, they all have a higher compute performance in terms of arithmetic performance, and they also have a higher bandwidth. So both has improved, the compute performance and the memory performance, but the compute performance has improved to a much more significant level than the memory performance. And what we have is that we suddenly have a machine balance that is larger than on the previous system. And what we see is that our algorithm, while the arithmetic intensity of this algorithm didn't change, that the algorithm that was previously compute bound is now memory bound. So it's running into the memory limited performance. That also means that despite we had a pretty significant performance improvement in terms of peak from this system to that system, the performance improvement that we see for our algorithm is significantly smaller. So now the communication is the new bottleneck, and how we get the data into the processing units. And this is also called the memory wall that is coming towards us, that we basically have, or we see a trend where the compute performance is growing faster than the memory bandwidth. What we did in my group was we kind of took a step back and thought of, okay, what is all this model based on? It is based on the strict coupling between the precision format that is used for the arithmetic operations and the precision format that is used for the memory access. But maybe that is no longer the way to go, because we see that the computing is getting more cheaper and cheaper, and the memory access is getting more and more significant in the overall performance. So in that sense, we should have algorithms that compute in a very low precision format, that compute in a very high precision format, because the computations are for free anyway. But when it comes to main memory access, we should try to make sure that the data is compressed as much as possible, such that we kind of try to remove the pressure from the memory bandwidth. And the idea is basically to have something that we call a memory accessor. And this memory accessor, you could also see that as a compression entity that is sitting between the arithmetic units and the main memory. And whenever I read data from main memory, this data comes in a compressed format. The memory accessor basically decompresses that into, for example, double precision. Then I do my computations, and before I write it back to main memory, the result, I compress it again. And this compression, that can be lossless compression, like Huffman encoding or any of the sophisticated compression algorithms, or it could be lossy compression. So for example, we just cast the values to a lower precision format. And if we realize that in this roofline model, what we basically do is we push upwards that bandwidth limited performance. Why is that? Because suddenly we can do more operations with for algorithms that have the same arithmetic intensity if we define the arithmetic intensity in terms of floating point operations per data access. So far the theory. So does that actually work in practice? So what we look at here is an NVIDIA A100 GPU, which is the current or the latest GPU from NVIDIA for servers. And what I indicate here is the peak performance for double precision, so that is the lower line, and then the peak performance for single precision, that is the upper line. And what we are now doing is an experimental roofline. So we have an algorithm where we can vary the arithmetic intensity, and for different arithmetic intensities and running either in single precision or in double precision, we get these rooflines. So the red one is the roofline, the experimental roofline for double precision. And then the green one is the roofline for single precision. And what we can also see is that this algorithm, where we can vary the arithmetic intensity to really figure out the experimental roofline, it pretty much reaches the theoretical peak of this architecture, both for double precision and for single precision. What we now do is we use our accessor and we say, okay, we do all the memory operations in single precision, but the computations we use double precision. And what we get is this roofline. Of course, if we are in the compute bound area, so we have an arithmetic intensity that is larger than the machine balance, then we are entering this region. So we're approaching the double precision peak. However, as long as we are in the area where we are memory bound, we actually achieve higher precision, higher performance than the double precision roofline. We actually exactly match the single precision roofline. So in that sense, it is successful. And if we now have an algorithm that is using double precision in all computations, we would, in the standard algorithm implementation using double precision memory access, reach that performance. And if we now, instead of using double precision read and writes, we use the compressor and compress the data before doing memory operations, we actually achieve this performance. So that is a benefit. But the question is that at all useful? And for that, we want to quickly think about the characteristics of an algorithm or a routine that actually is based on the memory accessor. So if we design that such that the memory access uses low precision, but the computations use high precision, then we get, for memory-bound operations, we get the performance of the low precision routine, because all the computations, you don't see them. At the same time, all the arithmetic is executed in higher precision. So we should, for all the accumulations that happen in processor registers, we should get a little higher accuracy. So we can think of two use cases. One is we could say, OK, we replace all the single precision BLAS routines, all the low precision BLAS routines, with memory or accessor-based BLAS that gives us a little more accuracy, but achieves the same performance. And the second use case is, if we can accept the loss of some information, we maybe want to replace high precision BLAS with this accessor-based BLAS that uses the memory accessor for the data access to the main memory. So let's look into the first usage model. What we look at here is the performance of the GEMV, so dense matrix vector multiplication, on a V100 GPU, that is the Summit GPU. And what we have here is the dark red line, that is GEMV using double precision. For comparison, we also show the performance for the Kublas implementation, that is the orange line. And yeah, so it achieves maybe 110 gigaflops, something like that. The single precision GEMV, blue line, and the purple line, the Kublas implementation, achieves roughly 220 gigaflops, maybe 225 gigaflops. So basically a factor of 2. And now the Accessor-based GEMV, that is the blue line, it perfectly matches the green line. So it achieves the same performance like the single precision GEMV. But it does all the accumulation in double precision, all the arithmetic in double precision. So you may now hope that you get a little higher accuracy of that routine. And if we look at uniform random values between -1 and 1, well, here is the error for the single precision GEMV. This is the double precision GEMV. And yes, the accessor-based GEMV gives you a little better performance, but it's really not that significant. And now the question is, where does that higher accuracy come from? And it actually comes from the fact that basically for each row, what you're doing is a dot product. You multiply your row vector with the right-hand side vector. So maybe we can push that experiment a little further by saying we don't look at the GEMV, but we actually look at the dot product. So left-hand side, again, the performance. And we see that, yes, indeed, the performance of the blue accessor-based dot product is pretty much identical to the performance of the 32-bit dot product, and pretty much exactly a factor of 2 higher than the performance of the 64-bit dot product. Now, on the right-hand side, we again show the relative error. And again, we look at uniformly random values between -1 and 1. And we see yet, yes, again, the dot product using the accessor is a little more accurate because all the accumulation is using double precision. But still, it's far away from the double precision dot product. And the reason here is that even though the accumulation is happening in double precision, in the end, I still write out the result in single precision. And the rounding that is happening there has a big impact. Now, if we look at different distribution of the values, and now we're looking at uniform random values between 0 and 1, the picture changes completely. And what we see is that now the accessor-based dot product achieves accuracy that is much closer to the double precision dot product than the single precision dot product. So in this case, we actually can gain a lot in terms of using the accessor-based dot product. Again, this comes for free. So in terms of performance, we don't have any performance differences. And I'm sure you can generate other distributions where this can, I'm sure you can even push it as far as actually achieving the accuracy of the double precision dot product. It just has to be the situation where the rounding from single to double, the final rounding does not, from double to single, does not introduce any error. So that is one use case for this accessor. We can basically get a little higher accuracy without paying any performance price. Now let's look at the second use case, and that is maybe even more interesting. So the idea here is we have a high precision, or we have an algorithm that uses high precision, for example, double precision. And we now want to accelerate this algorithm by using the memory accessor for some parts of the algorithm. But of course, we have to understand that this usually has impact on the final accuracy. So in general, it is not possible to just say, OK, I take my high precision algorithm, and now I use the memory accessor for all the memory access, and I see the same application output. However, in some cases, it is possible that you get the same application output. And in particular, it can be possible to get the same application output if you are careful with what you're doing, and you kind of adapt your algorithm to knowing that you're using the memory accessor. And I want to give you two possibilities that we experimented with, where the memory accessor can actually be very useful in accelerating algorithms while still providing the same output. And that is, in the beginning, self-healing iterative methods, and then the second part, approximate linear operators. And I want to start with the self-healing iterative methods. And the iterative method we are looking at into is the GMRS Krylov solver. So in general, the idea of a Krylov solver is to generate a subspace and to approximate a solution in that subspace. And I try to visualize that here. So we're looking for the solution X star. And here we have a one-dimensional subspace that has only one dimension. And this is the Krylov vector K1. And then this approximation would be the orthogonal projection into that subspace. And obviously, that is not a very good approximation. Now we can extend that subspace to actually have two dimensions, and then the solution approximation may be something better. And the idea that we now have is to say, OK, this type of method is memory bound, because in the end, what we have to do is we have to read and write often these Krylov basis vectors. What if we actually compress these Krylov basis vectors such that we use the memory accessor for storing and reading them, but still do all the computations in double precision? What happens is that the Krylov basis vectors are somewhat perturbed through the compression. However, we can hope that as long as this perturbation is not too dramatic, then we will probably only see moderate effect in terms of convergence delay. And maybe that convergence delay can be compensated by increasing the dimension of the Krylov subspace. And what we did is, this is kind of what we hope that we see, and this is actually a test matrix from Sweet Sparse. We first want to point out that we here look at modified Gram-Schmidt-based GMRS using double precision in everything. Then we also look at classical Gram-Schmidt using double precision for everything. So this is the green stars and the yellow stars. And this is basically the reference implementation. And then we use the approach where we compress the Krylov vectors using the memory accessor. And we use different approaches where we either use FP32, FP16, so half precision, or even some awkward integer formats. And then we should, in the best case, see no convergence delay, or only moderate convergence delay, or convergence delay that we can probably not compensate anymore. Of course, it's not sufficient to look at one single test matrix. So what we did is we chose a whole bunch of test matrices from the Sweet Sparse, and we did the following. First, we looked at what is the final residual accuracy that we can get. And what you see here is the comparison, again, modified Gram-Schmidt-based GMRS using double precision for everything, and classical Gram-Schmidt-based GMRS using double precision for everything. And this is basically what we aim for. This is these yellow stars / green stars this is the reference solution. This is what we want to achieve. And first, before we are evaluating that accessor-based approach, we want to make clear just switching to single precision would not be an option. So this is the single precision GMRS using modified Kalm-Schmidt, and you see that the final residual accuracy is significantly less than the residual accuracy for the double precision approach. So these orange circles are always quite far away from the accuracy that double precision GMRS provides. However, and here I look at the blue triangles, using a GMRS with doing all arithmetic in 64-bit, but storing the Krylov vectors in 32-bit, we actually get the same accuracy. So that is really cool. We always get the same accuracy like the double precision GMRS, using also double precision for storing the Krylov basis. And now the question is, maybe we need some additional iterations. Are we in the end faster or are we slower? And this is what we show down here. So that is the speed up over the double precision reference implementation. And what we see here is that the blue triangles, they are scattered, and some of them are actually lower than 1. So these cases are, in fact, cases where we have a slowdown because we need additional iterations, and they cannot be compensated by the faster memory access. But in general, we see on average a speed up of 1.4x over a double precision GMRS. So that means for all these test cases that we looked into here, we see a performance benefit when storing the Krylov vectors not in double precision, but in single precision. And then we, of course, also looked into what happens if we use half precision. And it turns out half precision, these purple triangles, we often do not achieve the same accuracy. And then we looked into what happens if we do some awkward conversions of the values and storing them and integer values, 32 or 16-bit, and the results are mixed. So overall, our takeaway was that maybe using single precision is a good compromise between additional iterations while still preserving the accuracy of the final accuracy and getting a good speed up. Of course, if you have a specific problem, you can play around with it and tune the precision format that you use for storing the Krylov basis to get the best speed up. So that is self-healing iterative methods and how they can benefit from using the memory accessor. And there may be even more general usage for the memory accessor is approximate linear operators. And I, in particular, think of preconditioners. So a quick recap. The idea of a preconditioner is that instead of solving a linear system ax equals b, I solve some system a tilde x equals b tilde that I get by multiplying both sides or applying a preconditioner for both sides of the equation. And this preconditioner p, or p minus 1, is a rough approximate inverse of the matrix A. Of course, I would have the solution right away if P inverse would be A inverse, but that is not realistic because inverting the matrix A is way too expensive. So in most cases, P is only a rough approximation. And one example of a preconditioner that is often only a rough approximation is the block Jacobi preconditioner. The block Jacobi preconditioner basically looks at a linear system, identifies blocks that lie on the main diagonal, inverts them, and pretends, well, that is a rough approximation of the matrix inverse. And it's true. Assume that we would not have any of these off-diagonal elements, then the preconditioner would be the exact inverse. But as we have usually quite some elements of the main diagonal blocks, it's only a rough approximation. And as you can imagine, the larger the blocks, generally, the more accurate is your preconditioner, but also the more expensive is it to compute the preconditioner. In most cases, in most scientific application, one tries to map the blocks to some matrix properties. So for example, if you have a finite element simulation, the blocks naturally arise from the finite elements. the unknowns that are associated to the same element. Now, if we stand here and figure out, okay, in most cases, this block Jacobi preconditioner is just a rough approximation, why should I use high precision for storing that preconditioner? So why can I not say, okay, I cast that preconditioner to lower precision, and I probably still have the same accuracy of the preconditioner, but I can access it much, much faster. And this is exactly what we are doing. So we are taking these diagonal blocks and storing them in lower precision. However, we have to be very careful. Because we have to preserve the regularity of the preconditioner, we have to check for each diagonal block, or each inverted diagonal block, what is the condition number, how much accuracy of the preconditioner do I want to preserve, and what is the value range. Because if I cast to single or half precision, it could also happen that I run into overflow or underflow. So I have to be a little careful, and that is exactly what we do. So we look at each of the diagonal blocks, we check the condition number, and we check the exponent range, and then depending on these properties, we select a storage format that is suitable for that specific block. Might be different for other blocks in the same matrix. So by doing this, we can make sure that we preserve the regularity. Also, and that is different to just using a low precision preconditioner, we still use double precision in all arithmetic operations. So all computations still use high precision. It's only the data format that is used for the memory operations that is different. Because otherwise, we would not have a constant operator anymore, and we would need a flexible Krylov solver, and that makes everything a little more complicated. But by using the memory accessor and using still high precision in all arithmetic operations, we still have a constant operator. The downside, of course, is I have some overhead. I first have to look for each diagonal block. What is the condition number? What is the value range? Which format can I use? And then I also have to store that information. And as you can imagine, that makes the whole thing very problem dependent. And this is actually also what I can visualize here. So assume I have a set of matrices, and here I look at one first from the sweet sparse matrix collection. I look at all the different blocks, and in this case, I figure out I can store all these diagonal blocks in half precision without destroying the regularity of the preconditioner. That may be different for a different matrix. So here I need to use double precision for storing the diagonal blocks. Otherwise, the rounding from double to single or half precision would destroy the regularity. And then for some other blocks, I can use single precision. And in the end, if I look at a big set of matrices, the picture is very mixed. So some matrices, you really need to use double precision. Some other matrices, you can store a significant portion of the block Jacobi blocks in lower precision. I want to show you how that works in Ginkgo. So what we see here is, again, the Apache 2 problem that I previously looked into. It has a condition number of 10 to the power of 7. And if I use a double precision conjugate gradient solver and a double precision preconditioner, I get an accuracy improvement of 10 to the power of 9. And that is exactly according to the expectations, because there's this rule of thumb that tells me the relative residual accuracy is roughly the unit round-off times the linear system's condition number. Unit round-off for double precision is 10 to the power of minus 16. Condition number 10 to the power of 7 gives me 10 to the power of 9 in terms of relative residual accuracy. Ginkgo allows to also run in or to compile in different precision formats. And if I just run the same setup in single precision, I see like this is not converging anymore. And that is again according to the expectations, because the unit round-off for single precision is 10 to the power of minus 7, and I have a matrix with condition number of 10 to the power of 7. So I have a relative residual accuracy of 1, so no improvement. What I'm now doing is the double precision CG, and a double precision and a mixed precision preconditioner, where for each block I figure out which precision format I use to store this specific block. And what I can see is that I preserve the convergence. So the accuracy of the solver is the same like doing double precision CG plus double precision preconditioner. And if I look at the runtime, I'm actually roughly 15% faster. And that is because the access time to the preconditioner is faster. Nicely, or this is integrated into Ginkgo, and you don't have to even analyze the diagonal blocks by hand. This is all done automatically. If I now look at the complete set of test matrices, I show here the iterations, and I show the speed up, and always numbers above 1 are good. So numbers below 1 means for the iterations that I need additional iterations. And there are actually a few. And this is block diagonal systems. So the preconditioner was the exact, or more or less exact inverse. And if I now use lower precision for storing the information of the preconditioner, I lose information, and I need additional CG iterations. However, for most of the systems, I'm faster, and on average, we have something like a 16% speed up. We can, of course, use the exact same approach for other preconditioners. And here I have an example for incomplete sparse approximate inverse. Again, we compute the incomplete sparse approximate inverse. And in the end, what we do is we store the sparse approximate inverses in lower precision. And we evaluate the efficiency of that. And we see here for incomplete sparse approximate inverse and factorized sparse approximate inverse that we, on average, have like a 15%, 10 to 15% speed up of the preconditioner if we store the preconditioner in single precision. And if we store the preconditioner in half precision, we even have like a 20 to 25% speed up, but some cases where we lose convergence. And that is, we think, because we lose regularity, because for that algorithm, we haven't figured out a possibility how we can quickly check that regularity is preserved. For the block Jacobi, it's easy. You just look at the different blocks and check whether the condition number is, and check whether the regularity for each block is preserved. For an incomplete sparse approximate inverse preconditioner, we haven't found a quick way of checking whether regularity is preserved when casting to a lower precision format. And with that, I want to summarize what we did. So we see a strong need to decouple the arithmetic precision from the memory precision. And we have to do that using on-the-fly compression of the data. So that means the memory accessor has to act on data that is in processor registers and compress that before invoking memory operations. In many cases, we think that this needs to go hand in hand with re-engineering the algorithms such that they actually know that we are using the memory accessor. We have shown that for accessor-based BLAS, this can give an accuracy improvement over the BLAS1 and BLAS2 operations without impacting the performance. So we get the same performance, but better accuracy. And we have also seen that for the other way around, if we allow for some loss of information, we can accelerate algorithms by using the memory accessor for still computing in double precision, but compressing the data before reading and writing from main memory. Moving forward, what do we need to do next? We started with GemV and dot product. I think we want to have complete coverage of all BLAS1 and 2 operations. And Thomas, one of my team, is currently looking into TRSV. And we think that their accuracy also plays an important role. We also have to look more into non-standard formats that is tuned for data. So assume that we have a data that is arising in some operation where all values have the same exponent. Well, we could just cast away we could just cut away the exponent. We would store this as a reference point, and in the data compression, basically just the exponent is cut off. That would save us some bits in terms of what we have to communicate to main memory, and we would accelerate without losing any information. There exist sophisticated compression techniques like ZFP, SZ, and so on that have a very high compression ratios while still preserving much of the information of the data. And we have to check whether we can actually use them. The challenge there is that they usually use interpolation and other sophisticated tools that you can use if you have a large data set that you compress at a time. We can't really do that because all the compression has to happen in processor registers. So if we would first accumulate data in main memory and then at a later step compress it, we would lose all the benefits. So we have to do the compression in processor registers, and processor registers are a scarce resource. So we probably wouldn't be able to keep a lot of data in processor registers and then apply sophisticated compression techniques, but we have to look into it. And then I think there's a lot of potential in looking into other algorithms and applications that can benefit from the memory accessor. In the end, I want to point out there is an effort in the US exascale computing project that is actually looking into what is possible if we use multi-precision and mixed precision algorithms. How much can we gain in terms of performance, and how much is also possible in terms of increasing the accuracy beyond double precision. And just last year, there was a very comprehensive report that was published, which is basically a survey of the landscape in terms of what exists and what are promising paths forward for developing mixed and multi-precision algorithms. And the memory accessor is sure one of the very promising research directions. And with that, I thank you for your attendance and welcome questions.
Thank you very much, Hartwig, for this very interesting and entertaining talk. All right, questions. Please raise your hand in the Zoom toolbox. There's a raise hand tool to indicate that you want to ask a question. Okay, so I have a question. Maybe I didn't quite get it, but how do you exert proper control of the generation of stores when the code is generated? Because depending on exactly the code generation process works, you may not have control over each and every store that happens in the code. So how do you make sure that only those stores, well, that all the stores that should go to memory get the compression, and all the others, maybe because you get register spills, for example, they do not get compressed because you don't want that? Or is it not a problem at all?
So I would have to pass on this question to Thomas, who did all the heavy lifting and actually implementing that. But as far as I understand, it is so far not a problem at all. That might be also because of the algorithms that we are currently looking into. But maybe, Thomas, you can say something to that. Actually, Thomas isn't online. So I guess I then have to, delay that question, and I could come back to you. But so far as I know, this has not been a problem at all. So important is that all the reads from main memory happen in the compressed format, and then you do a casting or conversion in the processor register. So you read it into a register, you cast it, and then you use it in your arithmetic operation.
Okay.
But the question of whether at some point I run into too much register usage, and then, for example, on a GPU, I lose in terms of occupancy, that is a valid question. I think for the problems we looked into, that was not a problem.
Yeah. Okay. There's a question by Nathan.
Just a very basic question from your beginning. When you were talking about the memory bandwidth versus CPU speed, I think it was, and you're plotting how they've been growing, or
I will just go back. Yeah.
Yeah, I think it was your first or second slide.
Yep.
Yes, when you're talking about the bandwidth limits, you're talking about limits from RAM to the CPU, yes, as opposed to, say, what is it, M1, M2 kind of?
Yes, that is true. So it is main memory to processor. So it doesn't account for cache levels and so on. So this is what you would get as main memory bandwidth. Yeah.
Yep, and the cache levels, I'm guessing, are a lot faster, so aren't any threat of bottleneck.
Yes. So that is really for algorithms that are entirely memory bound. So I do understand that in many applications with a sophisticated cache hierarchy and prefetching, you might get better bandwidth for your application. Yeah.
And is this to, say, standard RAM or GRAM when you're, what is it, GDD?
I would have to ask Mark Gates, who created that figure, but I'm pretty sure it's main memory, so standard RAM.
Okay.
Yeah. Well, respectively, the RAM that you have on the respective device, like V100 or KNL or whatever. Yeah.
I guess I'm asking if you've got a cluster made up of video GPU, just standard video cards. Is it from the on-card RAM, which is the graphical?
Yes. So it is not the
R5 or whatever.
Yeah. So it is not the bandwidth from main memory CPU or main memory host to V100 or whatever GPU. It is the bandwidth between the GPU main memory, so the processor main memory, and the arithmetic execution cores, where the arithmetic actually happens. So it is the GPU memory in that case.
Okay, thanks.
Okay, Olaf.
Yes, can you hear me, Hartwig?
Yeah, sure.
Yeah. Okay, good. I have one question related to the title, which I'm noticing is now, it's called Modular Precision Ecosystem.
Yep.
Could you please motivate this a little bit? Where is actually this ecosystem coming from? And you have not talked about applications. And I guess this is also part of this. Maybe you could give us some comments or some.
Yeah. So in the best case, we would have an ecosystem where you can have not only different precision. So today I talked mostly about double precision and single precision. So there are many other precision formats out there that you can make up. Also creating precision formats that don't exist anymore. And in the best case, you would actually have the compiler taking care of all that. So the compiler would figure out which precision do you want to use for main memory access, which precision format do you want to use for arithmetic operations. I'm not a compiler person, so I can't tell you whether that is possible or not. Some people tell me, yeah, that might be possible. Yes, and ecosystem in the sense that maybe at some point you can just plug and play precisions together.
Olaf, you're muted.
I noticed, yes. Thank you. Could you please let us know more about the applications that you have in mind or that you have been working on where these techniques are being used?
We can't currently report, so we don't have any applications that you're using that. So okay. That is, let's say, pure research at that point. Yeah, okay. But I'm sure there will be. I mean, any of the problems where these matrices come from should potentially be candidates for something like that.
Yeah, I mean, I'm asking because I noticed half of the matrices comes from my group, which you're listening in your. In the benchmarks, and so these benchmarks come from automobile sheet metal forming simulations, which are very hard to solve. But there are a lot of groups where a factor of 1.5 or 2 would be very appreciated. Okay. So maybe I will come back to you on this.
Which only shows that you have a very significant presence in the Sweet Sparse Matrix collection.
And I don't know, but at least there are some matrices exactly. Yeah. Okay. All right. Thank you.
Okay, Raju.
Hello, can you hear me, George?
Yes.
Yeah, so I have a question. In which precision do you save the data structure for example, the residual vector or the CSR matrix, is it single precision or double precision? And the second question, how do you convert that? Let's say if you save them in the double precision, how do you convert them to single precision during the read operation, but during the computation, you preserve the double precision?
I hope I understand the question right. So the question is, first of all, what precision format do I use for all the other operations and for storing all the data? And that is double precision for everything except for the Krylov vectors or the preconditioner. For everything else, I use double precision for computing, storing, reading, everything. And the second question is, how do I do the conversion? Is that correct?
Yes, yes.
So in fact, I use a cast function for that. So I cast from double precision to single precision. I guess in most cases, it's just cutting off the bits. So if you cut off the significant, the bits that you don't use, if there is a high performance conversion routine available in that on that platform, we use that one. If we convert back from single precision to double precision, it in fact doesn't matter what is added in terms of bits. So you could add anything. You could add, I guess, even random numbers, and it would still work. Okay, except for it always has, if you do like the iterative method and you use the adaptive precision preconditioner, you can add random numbers for those bits that you fill up, but it always has to be the same bits. So in each iteration, the preconditioner has to be constructed out of what you read from memory and then adding bits as you want.
Okay, so for example, in the case of, let's say, LU preconditioner, then I would store the L and U and all these Krylov operations in the single precision, and the other GMRS solver operations, I would store them in the double precision, right?
I'm not sure I understand your question. So for the GMRS, you would store the Krylov basis vectors in single precision, but cast them back to double precision when you're doing the operations. And then your question was about the preconditioner, the ILU preconditioner.
Exactly, exactly.
So first of all, I don't think that you would see any benefit from doing that to an ILU preconditioner, because an ILU preconditioner, the sparse factors are stored usually in CSR format or something like that. Exactly. So you have significant overhead in terms of the indexing. So you wouldn't really gain a lot by casting the values to a lower precision format. However, as long as you preserve regularity, maybe you could win something, and you may try that out. I think so. We are successful or somewhat successful with the block Jacobi preconditioner, because there we don't carry around indexing information. So we only have the diagonal blocks, and the larger the diagonal blocks are, the more values do we have that we store in lower precision. So we have actually a significant impact on the application time. If you have a CSR-based incomplete LU factor, and you would use single precision, I guess you would probably get like a few percent from that. But you try it out, please.
Yeah, because I'm working on this multi-level nested dissection ILU preconditioner. So I was thinking if I could use this approach in because we have a templated data type, and it would be not so difficult to use this approach. So that's.
Yes, but be careful. So the computations still need to use double precision. So I'm not sure whether you're templated on the memory precision and the arithmetic precision. If you are, you can sure do that.
Yeah, thank you. I will have a look at your papers. Yeah, thank you.
Another one from Nathan.
So I was just thinking, so I'll preface this by saying that my experience with low-level coding is very limited. So I was what I was wondering was, in some scientific computing situations, you might have chaotic systems where you definitely want to keep the precision, because any loss of precision could make your calculations veer massively off. So I was curious, is there a, if I understand it correctly, how you'd work with this kind of high precision code is you'd find some kind of encoding for each of your variables and you'd store that, and then you'd do a decoding and then do the calculation, and the decoding essentially comes for free because you've got all the spare CPU time that you can't use. Or does your code or have you written code which automatically does this for some arbitrary data, so it figures out how to encode it and store it so you can quickly pull it out? Or could you give a kind of intuition as to how that works in general?
So thanks for that question. So there is an effort, anyone on the call can correct me if I'm wrong, but I think it's coming out of Sherry Lee's lab that looks into how precisions or the use of precision can be optimized in a complex application. And that is basically a sensitivity analysis. And it tries to find or to locate areas where you can use a lower precision format without changing the application output. We are not doing that yet. I'm not even sure whether we will do that. I think that is not easy, and I'm not sure how much success they have. What we do is currently we sit down and think, okay, which part of an algorithm could be stored in a lower precision format without harming the final accuracy. So we rather take the theoretical approach, pen and paper, and figure out, okay, the preconditioner, assume it has only a certain accuracy. We may be able to get away with casting it to lower precision to speed up the computations without impacting the final accuracy. What we don't do is, again, that we have an automatic process that tells us you could do this XP and this dot product in lower precision without impacting the accuracy. We don't do that yet. Or maybe we'll never do that. I don't know.
Okay, it sounds like I'm misunderstanding something here. My original thoughts was that you'd say figure out some, my original thoughts of how this might happen is that you'd have some code which recognizes a pattern in whatever floating point numbers you want to store and then encodes it that way losslessly. But it sounds like the work here is...
Okay, I have to, okay, maybe my statement was a little confusing. So if we have a component like the block Jacobi preconditioner where we say, okay, we accept some loss of information that is coming from using lower precision storage, then our code figures out for each block what is the right format that we can still use without breaking the algorithm and getting the final accuracy, but speeding up the application. But that is still a small part of the algorithm. It is not the approach, and it is like one component, one linear operator in that sequence of operators. It is not the approach where you just have a black box algorithm, give it to some tool, and the tool actually figures out that could be stored in lower precision. Does that answer your question, maybe?
And maybe I can add some
I think it's a little
here.
bit different, but maybe I'll send you an email or something and get the actual name of the lab in case I misspelt.
Hartwig, maybe I can add some comment here.
Sure.
So for now, we do not use like any encoding technology like DFP. So we always use the IEEE, the floating point as the low precision. So it's not, we do not do exactly the encoding or decoding in on the fly. We just cast it somehow.
Yeah.
But,
yeah. So exactly. Yeah.
Okay. Are there any more questions? If that's not the case, I would like to thank the speaker again. Obviously, the topic has raised a lot of questions and interest in the audience. That's nice to hear always. So thank you again, and goodbye, everyone. See you next time. Bye-bye.